Hi, this is Kara Tierney from Monroe Community College, and in the last video we were talking about heats of reaction and heats of formation. In this video we're going to talk about how we can use those heats of formation that you can look up in the appendix in your book in order to calculate the heat of reaction for a particular reaction. So how we use that is we can find the heat of formation values of your reactants and products in your book. Usually they will be given to you in a table form, and then we can insert them into this equation in order to calculate the heat of reaction for your particular reaction. These symbols here, these represent the sum of, and then the m and the n, those are the coefficients for the reaction equation. So basically you're going to take your products minus your reactants, and for each product and each reactant you're going to multiply the coefficient from the reaction equation by its heat of formation. So let's just start a problem now. Example problem 4 says to determine the heat of reaction for the combustion reaction shown below. You are given the heat of formation for 3 of these materials involved in this reaction, and if you notice there's no heat of formation for oxygen. The reason for this is that the heat of formation for any element in its standard state is equal to 0. So for this calculation, the heat of formation for oxygen is 0 because it's diatomic and it's in its standard state. Knowing that, I would like you to try and start this problem plugging the known values into the equation given in the last slide. See how far you can get. I will show you how to approach the problem when you return. If you calculated an answer, compare it with this answer. Notice that there are 5 significant figures in the answer, and if you did not get the right number of sig figs, you're definitely going to want to watch how I calculated this problem, because your significant figures will count towards at least a point on an exam. So our heat of reaction, if you recall, is equal to the sum of the products minus the sum of the reactants. So let's tackle our products first. So our first product is CO2, and because it has a coefficient of 2, we're going to put 2 moles, and we're going to multiply that by the heat of formation of CO2. Now I will be plugging this in a little bit, but I just want you to know where all of these numbers come from. Water also has a coefficient of 2, so we're going to multiply that heat of formation by 2. I'm going to start on the next line. If you notice, the states for each substance is given, and in this case it's all gases. Make sure if you're looking up any values that you need to make sure that the state is correct. A gas will have a different value than a liquid because a gas requires more energy to produce. So for the next set of numbers, we're looking at the reactants, and C2H4 doesn't have a coefficient, so we're going to use that as 1, and that is for C2H4. And oxygen has a coefficient of 3. Now, if you recall, the heat of formation for oxygen is equal to 0, so we know that we can just cross out this part. And so we're going to plug in our numbers now. So we've got 2 moles times negative 393.5 kilojoule per mole. Notice that the moles cancel out. We're going to add this to 2 moles times negative 241.8 kilojoules per mole. Once again, those moles cancel out, and we're going to subtract from this 1 mole times 52.3 kilojoules per mole. The moles cancel out. So if we do these multiplications, because it is a series of multiplications and then additions or subtraction, Do each combination of numbers first. So I'm going to multiply these first and write that out. And you need 4 significant figures. These coefficients have infinite sig figs. So we have negative 787.0 kilojoules plus, now the 2 times negative 241.8, that gives us negative 483.6 kilojoules. And we are subtracting 52.3 kilojoules. And all of these go to the ones place, so when we add them up, and it looks like I don't have room, so I'm going to write it right over here. You should get negative 1,322.9 kilojoules. That's why there are 5 significant figures, because each of these goes to the tens place, and when you add, you need to stack them up vertically and go to the smallest place. So we go to the tens place. What I would like you to do now is do the your turn problem, where you're going to do the same thing. I want you to calculate the heat of reaction for the oxidation of ammonia shown below. I've given you the heat of formation for everything that's needed. Remember that the heat of formation for oxygen is 0 because it's in its standard state as an element. So try this problem by yourself, and we'll discuss the answer when you get back to class. There is one more video left in this series before you go to class, so be sure to watch that next.